slideshow that you had the other day. This is where we left off. We've got Bert playing pool. And it says Bert strikes a cue ball of mass 0.17 kilograms, giving it a velocity of 3 meters per second in the x direction. So they went ahead and helped us out and said, let this be in x. Okay. When the cue ball strikes the 8 ball, previously at rest, the 8 ball is deflected 45 degrees from the cue ball's previous path. So I would say that that's 45 degrees above horizontal. And the cue ball is deflected 40 degrees in the opposite direction. Find the velocity of the cue ball and the 8 ball after the collision. Okay, so we don't have either one's final velocity. We don't have either one's final momentum. We do have both angles. So this is a little different than we were, I guess maybe, what day? Tuesday? Did we work on Tuesday? This is a little different than Tuesday because in those problems, they had given us the final velocities, but not the angles. Okay? The relationship still holds. So if I were you, I would write down a lot of this information right here. Okay, you need to know the mass of the cue ball. So M1 is 0.17 kilograms. V1I or V1 naught is 3 meters per second. M2 is 0.16 kilograms. V2 final, we don't know. That's what we're looking for. We know that the angle for that ball is 45 degrees. M1 final, again, we don't know. Final velocity, sorry, not M, but V. V1 final, we're looking for. We know theta for V1 is 40 degrees. Theta for V2 would be, or M2 is 45 degrees. So I would get this information down on paper.
Would you say theta 1 is negative 40?
Yeah. You could say negative 40 or you could put negative sine of 40. I have a hard time calling it negative 40 because that doesn't necessarily hold true for cosine. Only the sine version would be negative. Do you have all of this down? No? Yes? No? No. Okay, I think we got really confused. Also, you can't have a blank slide in here unless there's something on it, so I put a B for blank. Now then, I think we got really confused with the momentum equations the other day. So simply put, the momentum of object 1 in x. The momentum of object 1 in x, that's the only object that's moving in this particular kind of problem. Okay, object 2 is stationary. So the momentum of object 1 in x is equal to the sum of the momentum of both objects in x in their final state. So whatever momentum it has initially in x is then shared in x by the two objects in the end. Does that help that make more sense? Okay. So when we look at that, that's going to be M1 V1 naught equal to M1 V1 final cosine theta plus M2 V2 final cosine theta. That means x. This would be cosine of angle 1. This would be cosine of angle 2. Okay? That's the breakdown there. I didn't mean for it to be confusing for you, but I think it was. Does this help a lot? Do you understand like where these numbers are coming from? This is cosine of the angle for angle 1 and cosine of angle for angle 2. And because this object, when it collides, then both objects continue moving to the right. So both of these angles are going to be positive angles because cosine is positive to the right. Yeah? Okay. So then in y, What is the momentum of the object in the first object in the y direction? 0. 0. That thing had no momentum in y. So the sum of momentums in y need to equal 0 by the time they're done. Okay, because conservation of momentum. It's got to equal 0. So we've got momentum of object 1 in the y direction finally, plus momentum of object 2 in the y direction finally. Now, how do I handle momentum in the y direction? Well, that's going to be m1 v1 final sine of angle 1 plus m2 v2 final sine of angle 2. And depending on which object goes in which direction, if you've got one traveling below the x-axis, and I think that's what happens on this problem, the cue ball ends up going below the x-axis. So this angle right here is going to end up being negative, right? That portion needs to be negative because it's headed down. Cool beans? Is that feeling better today than it did the other day? Okay. Now, I will tell you this. We don't have enough information right now. We're missing 2 variables. It would be very easy if they had given us, like we know one of them has this final momentum. Okay, that would make this a much simpler problem. But the problem is they didn't give us either one's final momentum. They didn't give either one's final velocity. So right now we have a system and we have 2 variables out. Anytime I have a system with 2 variables missing, what am I lent to do? Substitution, elimination, right? You can do a lot of things here. My brain usually goes to substitution. Okay, we need to solve or isolate for one of the variables, and then we can go back into the other equation with that information. Okay, so what I did whenever I worked this problem the first time is I took this second sentence. It seems smaller and less daunting. And I took negative m1 v1 final sine theta 1 plus m2 v2 final sine of theta 2, and I set that information equal to 0, which means that m2 v2 final sine theta is equal to m1 v1 final sine theta 1. Because they're equal to 0. And I isolated one of the 2 final velocities that I don't know. Do you have a preference on which one you'd love to solve for? Cool, let's solve for V1. V1 final, let's isolate that guy. Okay, are y'all following this? So that number is going to be equal to m2 v2 final sine theta 2 divided by m1 sine theta 1. Okay. So what we have here is v1 naught or v1 final equal to m2 was 0.16, v2 final sine of theta 2, I believe theta 2 was 45 degrees. So sine of 45 degrees divided by m1, which was 0.17, sine of theta 1. And now this is positive because we already handled the negative. Do you see what I'm saying? When we swung it across this equal sign right here, it became positive. So I would get a number instead of calling it all of this V2, because we're going to substitute it in. I would go ahead and get a number, and then we'll call it that number V2 final. So let's get this constant right here. We've got 0.16 times sine of 45 divided by 0.17 sine of 40. Anybody? 1.03 V2. 1.03 V2. Okay, so that's a relationship. We know V1F is equal to 1.03 V2F. So we can sub out V1 final in this equation in the top, and we'll call it 1.03 V2 final. And now we can isolate V2. You'll see where this is headed? Okay. So if I'm plugging into that top equation, M1 naught is, was it 0.17? And V1 naught is 3. So I got 0.17 times 3 equal to M1 0.17 times V1 final, which we're going to use 1.03 V2 final, cosine of angle 1, which is going to be 40, yes, cosine of 40, plus mass 2, 0.16 V2 final, cosine 45. I want to simplify these multiplication and decimals and all of that stuff. Okay. If I do 0.17 by 3, what do I have right here on the left side? 0.51 equals, somebody do 0.17 times 1.03 times cosine of 40. 0.17 times 1.03 times cosine 40. 0.135 V2 final plus, somebody else do 0.16 times cosine 45. .113 V2 final. Okay, now look, we can combine these. These are like terms. So we got 0.135 plus 0.113 V2. So 0.51 equals 0.248 V2 final. Now what? Okay. Do it over. 2.057. Yes, 2.06. Good. 2.06 meters per second. This is the velocity of the black ball after it's gotten hit. That's the vector. Okay, that's the vector. The direction we already knew was at 40 degrees or 45 degrees. That's the path of the 8 ball. That's our V2, right? So that's that 2.06. That gives us this number right here. We did. We used those components already, right? Yeah, so now we need V1. And Seth is saying if I come right here with that, I can get V1. We know that V1 is 1.03 V2. So multiply that number by those two numbers together. And then we'll have V1 final is anybody? 2.13, I think I got the first time, but I did some rounding differently, so. Okay. And so that gives us this number. So then they could ask you, what's the momentum? What's the momentum? We just found the velocities. We know the masses. We could find the momentums. They could ask me, what's the y value? What's the y component? And you know that that's going to be V2 sine 45. Or V2 sine 40 would be a negative option. Okay? You could use all of that information, and they could ask you 1,000 different kinds of questions dealing with this particular topic. The hard part is knowing these two relationships. And so if you needed to write anything down on this collisions in two dimensions business, that's the crucial part. You need to know that momentum in X is conserved. You need to know that momentum in Y has got to equal 0 because there was no momentum in Y initially. And then whichever way the problem takes you after that, you can handle. Do these feel better than they did yesterday or Monday or Tuesday, whatever day we did this? Yes.
Why are they both V2?
I meant to put V1 right here. This guy should be V1. Yeah, sorry. Good question. So we know now V1 was 2.13 at 40 degrees. Other questions that you guys have here? Anybody? Does that clear it up a little bit? Does that make it less muddy? I'm not getting a whole lot of yeses here. Hello? Should I breathe life into you? I'm not resuscitating today. I don't feel it. Are you okay? Yeah? Okay. All right, so let's go on then. Now we're looking at perfectly inelastic collisions in two dimensions. So earlier we did elastic collisions where the objects bounced and maybe they bounced in different directions. Okay? We know that if it's elastic, momentum is conserved. Momentum is always conserved. That was a trick question. If it's elastic, what else is conserved? Kinetic energy. Okay? Those are two things you have to know. This is an inelastic collision, so we've lost what? Kinetic energy. Have we lost momentum? No, not ever. Okay? And so what has happened here when these two objects collide is the momentum vector is going to be the sum of the two initial momentum vectors. Did you hear me? The momentum vector, the resultant, this should make you think Pythagorean all day long, okay? Let's have these two cars. Imagine these are two cars at an intersection, yeah? This one's not paying attention, and this one's got the right of way. All of a sudden, they collide. Which way do they go?
That way.
Don't they? I mean, if they collide, then the resultant vector is going to equal the sum of the original vectors. That's how that works. They don't collide and go backwards, do they? No.
Imagine if they did.
Imagine if they did. Imagine if they collided and then they went this way. Did they?
Really big.
Does that work?
I mean, if in one is a lot greater, but
And
it
there's
wouldn't
a
go.
sharp
It wouldn't go
turn
up
left.
like that.
Yeah, it wouldn't.
Lots.
It wouldn't. So we're going to Pythagorize here. Pythagorize, that's our verb of choice. And then we're going to use tangent inverse. It shouldn't be too difficult here. Okay. One thing that you do get to know is the velocity is equivalent to momentum divided by combined mass because it's an inelastic collision, meaning your masses stick together. Okay. So, yeah, well, what we know is momentum is equal to mv, right? Well, if I'm looking for velocity, final velocity, then that's going to be final momentum divided by entangled masses, m1 and m2. How's that? Pretty good? Theta is going to equal final momentum in y divided by final momentum in x. Tangent inverse of y over x, that's always the case. Rise over run. Y over x. Yeah? Think we can do it? I think we can. It's pretty straightforward. Okay, so we've got an object A traveling with mass of 20 kilograms. It's going to the east at 10 meters per second. An object B with a mass of 5 kilograms traveled south at 20 meters per second. They collide, they stick together. What is the magnitude and direction of the objects after their collision? And it feels like they go this way. I'm thinking. All right, so if we're looking at here, we know initial momentum in x is the same as final momentum in x, and in y, the same thing has to happen. Okay, they've got to maintain their velocities, and they've got to maintain their momentum. So let's try. We've got object A is mass 20 kilograms times 10 meters per second. So this is object A's initial velocity in x. This is going to be momentum in x initially. That's maybe 200. Maybe 200. Would y'all agree with that? That's this object's momentum in x. Secondly, we have the second object traveling with a mass of 5 kilograms, and he's traveling south at 20 meters per second. So that's a negative 20. This is our momentum in y initially. So that's going to be what? Negative 100 kilogram meters per second. Remember, momentum is a vector quantity. It has direction. So our final momentum is going to be the square root of initial momentum in x squared plus initial momentum in y squared, because that momentum has to be conserved. So we're going to have the square root of 200 squared plus negative 100 squared. Can anyone get us a number on that? Mm-hmm. 223.61 kilogram meters per second. Okay. So what was the question? What is the velocity, magnitude, and direction? So what did we just find?
The magnitude.
Of the
Vector.
momentum.
Yeah.
The question is, what is the velocity, magnitude, and direction? We just found momentum.
Divide by mass and find the angle.
Okay, so velocity final is going to be momentum final divided by masses, plural, because they're entangled, because it was inelastic. So we've got that 22 or 2,000, whatever, divided by 25. Why 25? It's 20 and 5. So 223.61 divided by 25.
Oh, I thought they were actually cars, and I was like, that's really light for some cars.
Yeah, 25 kilograms. Maybe marbles.
50 pounds.
8.94. 8.94 meters per second. And in what direction? How can we calculate this angle right here? Tangent inverse of what? Of momentum in the y direction divided by momentum in the x direction.
Negative 60. I'm guessing negative 60.
I'm not saying that. I'm gonna say 40.
So we've got tangent inverse of our momentum in the y was negative 100, and in x was 200. So tangent inverse of negative 1/2. We're in degrees.
Negative 26.
Yeah. Negative 26.57 degrees, or you could say 26.57 degrees south of east, right?
Yeah. Why does it go more right than down if the one on top is going faster?
Which one was more massive?
Oh, I forgot it's math. Okay, yeah.
Throwing.
I thought they were the same mass. When I made my guess.
Oh.
Yeah.
Swinging them out of the park. I'm over here just batting them back. Sometimes I get really scared in this class. Y'all throw questions at me that I'm like, oh, I don't know. Are we good on this one, though? We understand pretty well? Okay. Huh?
Time for it to get hard.
Time for it to get, yeah, here we go. Center of mass. So all we've been doing is dealing with objects that kind of their center of mass was in the center of the object. Either they were perfectly spherical, or they were particles that we imagined to be perfectly spherical, right? Or we treated the cars like they weren't Caminos that had like a long tailgate. They were just all little bundles of car that were nice, right? I say Caminos, and half of you are like, oh, what? Actually, we have different centers of mass, okay? This is why we teach linemen to bend their knees on the line. Why not? Why would they? What would happen if they didn't?
They're easy to topple over. Though.
Yeah, easy to topple over. If you'll lower your center of mass or your center of gravity, all of a sudden you're a lot harder to move, okay? It's about where the center is on the mass, okay? Did you know that every time you try to hang a picture frame, you're dealing with center of mass? Sometimes, like that one up there, see I've got it like on a string. If I were to move it a little bit over here, then its center of mass is off center, and it's going to hang crooked. So every time that you're trying to hang something straight, you're trying to find the object's center of mass. It's not hard to do when it's a perfect geometric shape. But let's say I wanted to hang a boomerang on the wall. And I'm going to have to really think about it. I'm going to have to find that boomerang center of mass in order to hang it so that it's straight as boomerangs go. Okay. Yep, I said that. Okay, here's how you find the center of mass. And this is a formula. Look, right here I said scavenger hunt on formula chart for center of mass. Here's what you do. Freeze. Look. You multiply the mass times the x-coordinate, and you sum it all up. Mass times x-coordinate, mass times x-coordinate, mass times x-coordinate. And then you divide by the summation of masses. You do the same thing in y. Mass times y-coordinate, mass times y-coordinate, mass times y-coordinate. And then you divide by the summation of masses. Okay? Look on your formula chart. Can you find it? Center of mass. It's got a little cm. And they tell you the formula. Multiply cm. Right here. Add up all your mass times x, divide by mass.
Why is it 3 mass?
It could be 79 masses.
Could be any, the ellipse, like the dot.
Yeah, it's infinite. All the way, and that's why you have the summation symbol. It means just add up as many as you have. As many as you have. Okay? Did you find it? Do you need to put your finger on it? Oh, yeah? Okay. This can also happen in a vector. So you could take its position vector and you could do the same thing. So that should lead you to this thought. If I can find center of mass on position, then I should be able to find the velocity center of mass by taking the derivative of the position ones. I should be able to find the acceleration center of mass. Okay? This gets really, really out there. Think fireworks. What's the center of mass of a firework where all of these particles are moving away from the center of mass? And got like indefinite number of particles. Infinite number of particles.
I don't want to calculate that.
Okay, cool. Once you find the center of mass velocity, you can find the momentum of the whole system by taking that velocity times the mass of the system. That's what this big capital M is right here. This is capital M for mass of a lot of things. Big M. Okay. Total momentum of a system of objects is equal to the total mass of the system times the total velocity of the center of mass. This system acts the same as if all mass was concentrated at the center of mass. So again, with the firework idea, you've got an infinite number of particles. And you've got the center of mass located like at the burst, right? But you can treat it once you have found the center of mass and you can find the momentum. You can treat it as if it hadn't separated.
So it's like all one thing still.
Right. It's a benefit. I mean, there's a huge thought here. If the momentum of the system is constant, no net external force is acting, then no matter what the individual objects are doing, the velocity of their center of mass remains constant. Hold on to that thought. If the momentum of the system is constant, then no matter what the individual objects are doing, the velocity of their center of mass remains constant. So you could think about like somebody with like arms and legs flailing for whatever reason, but they're moving forward, okay? No matter what arms and legs flailing are doing, what's the center of the mass doing? What's the object doing? Okay, so you can calculate as if they weren't. You could calculate as if they were running normally. I think, have y'all seen Friends? Do y'all watch Friends? You know when Phoebe runs through the park crazily? Yeah, and Rachel's so embarrassed because she's like, we should just run normally. So either way, velocities are moving as the center of mass should. Yeah, here we are. Okay, so if I could take the derivative and find velocity, then I could do it again, and I would have the acceleration of the center of mass. It works the same. It works the same. There are some, look at the firework. This is what I was trying to tell you. The below photograph shows 3 different firework rockets that were sent up into the air and then exploded. The center of mass of each rocket kept moving up, and the particles symmetrically spread out from each one. For each rocket, though, the velocity of the center of mass is equal to the weighted average of the velocities of each particle, resulting in the starburst pattern. It's so pretty. You see it? Okay. The acceleration of each particle and the center of mass all equal negative g. So they all have the exact same acceleration. And you could treat them as if they were still a combined mass. Pretty neat, if that's your thing. I wanted to go through these 2 problems with you. Okay? This is a lot more straightforward example of finding the center of mass than a firework. We have 3 different particles. I don't know why they're not hooked on together, but if I had to find the center of mass of these 3 particles in the x direction, x center of mass, I would take the mass of the first object, which is 3, times the x value, the x coordinate, 3 times 1, plus the mass of the second piece times 5, plus 1 times 7. I don't know why it's over there. 7. There's a 7 over there. All divided by the summation of their masses, 3 plus 4 plus 1. So the x center of mass is going to be 3 plus 20 plus 7. So 30 divided by 8.
Almost 4.
Okay. There's your x center of mass. Is that less daunting than the other pictures? Hope so. If you were going to find your y center of mass, you would take the y coordinates. So 3 times 2 plus 4 times 3 plus 1 times 1, all divided by 3 plus 4 plus 1. So 6 and 7 is 13, 14. 14 over 8.
12 plus 6 plus 1.
Did I do that? 6 and 7 and 1.
That's 4 times 3.
Oh, that's 12. 6 and 12 is 8 and 1. 18 and 1, 19.
Yeah.
19 eighths. See, that's a 9. 19 eighths.
You did it.
I did. Okay, so what does that mean? What does that mean? Well, if I had to hang this object on the wall, let it be these 3 weird independent pieces, I would locate the center of mass at 38ths. Let's see, that's almost 4. 1, 2, 3, 4. Almost 4, comma 19 eighths, which is a little bit over 2.
It's like almost halfway over 2.
So almost 4, little over 2. Here's your center of mass. Based on the information. So before we leave today, before I turn this class loose, I want you to find the center of mass of this object. That's your homework. Find the center of mass. And then Coop, you can go whenever you need to.
Go where?
To the counselor's office.